Hey guys, it's Miss Kennedy. Right now we're going to work on part of Standard 13.3, which has to do with interpreting graphing and motion. So there's really two types of graphs, distance versus time, or speed versus velocity versus time. What we're going to pay attention to is the distance versus time graphs. So we're going to take a look at Ashley's trip to Katie's house down there in the right-hand corner. First of all, I want to go back over some acronyms to help you remember how to graph. So let's take a look at the graph below. I see that a title, I see axes, I see axes labeled with a dependent and independent variable, and I'm also seeing a graph that is spread all the way through, okay, the grid lines. So thinking about this, there's two acronyms, and hopefully you remember this from Unit 1. So we're talking about dry mix, and we're also talking about tails. Dry mix, DRY, D is for dependent, R is for responding, and Y is for the Y-axis. The other, mix, M is for manipulated, I is for independent, and X is for the X-axis. So in this case, distance is on the y-axis with a unit, meters, and time is on the x-axis with a unit of minutes. Now let's talk about minutes. Minutes is not an SI unit, and we talked about SI units in Unit 1, so keep that in mind. Usually we report time in seconds, but in this graph we record it in minutes. Tails is also another acronym we can use. Okay, tails, T is for title. We have a title, Ashley's trip to Katie's house. A is for your axes, okay? You have an X and a Y. You also have I, which are increments or integrals. So if you notice that your line goes all the way through all the grid lines, it doesn't stop at the very beginning, it uses a small portion, it actually uses the entire graph. Very important, okay? L is making sure that your axes are labeled, so distance and time, and then S is your summary. In this case, our graph does not have a summary. Okay, so just remember our x-axis is our time in this case. It's a pretty key information. So what we're going to talk about a lot today is distance versus time, which is also equivalent to speed. Speed is the distance an object moves per unit of time, and we measure that in meters per second. Okay? So again, whenever we see a distance versus time graph, we know that we can calculate one's speed. So let's take our first example. Let's take a look at Ashley's trip to Katie's house, and let's talk about what her constant speed would be. Constant speed is the speed that does not change, but it remains equal over a given amount of time. So in reality, we see in this graph that constant speed happened twice. It happened between 0 and 4 seconds, and it also happened between 8 and 10 seconds. Okay? Remains equal over time. Got it? So let's do a first question. Ashley rode at constant speed for the 4 minutes of her trip. What was her constant speed? Well, again, our graph doesn't label speed. We have to calculate speed. So in this instance, we see that Ashley rode for 4 minutes. So let's find 4 minutes on our x-axis. Run our finger up, and you can see that it hits at the 800 for our distance in meters. So if we go back up to our speed, distance divided by time, so 800 divided by 4 is 200 meters per second. Again, make sure you have a unit, okay? Let's talk about average speed. Average speed is the total distance divided by the total time. So in this case, we're talking about Ashley's entire trip. Now, if Ashley's trip was broken down into a car ride, a bike ride, and say a walk, I could ask you her average speed during her bike ride, or I could ask you her average speed during her walk. But in this case, it doesn't specify this. It asks for her entire trip. So the total distance traveled is what? Looks to me like it's 1600 all the way at the top of the graph. Would you agree? All right, and then what is her total time? Total time looks like it's 10 minutes. Okay, so 16 divided by 10, you can see that she traveled 160 meters per minute. Okay, notice I said per minute, not per second. right? Now, if it asked you, you would have to technically convert, but we're not going that way, okay? The last thing I want to talk about with speed is there's something called instantaneous speed, and this tends to bother people. Instantaneous speed is something that occurs at a given point. So it's like taking a photograph. It's like a little snapshot of a run. And while you're in mid-run, that's your instantaneous speed. So it's the speed at a given point. So I could look at Ashley's trip and I could see Ashley's instantaneous speed at 5 minutes. So I find 5 minutes on the very bottom, her x-axis. I run my finger up and I see that she was at a total of 800. Everybody agree so far? So 800 divided by 5, again, is 160 minutes per meters per minute. Okay, so 3 different types of speed. Again, interpreting graphs is pretty important. So being able to understand what constant speed is and see it over time, if it's moving in a forward direction or a backwards direction. But if we take a look at Ashley's trip to Katie's house, which isn't discussed in any of the words given, we can see that I've totally lost my train of thought. Give me 1 second. Okay, so if we take a look at her, the total graph in general, but if we take a look between 4 minutes and 8 minutes, what happened in Ashley's trip? What did she do? It doesn't look like she traveled any further. It looks like she remained at 800 meters. So in that reality, Ashley took a break. She was tired. So she just stopped for a minute, for about 4 minutes, chilled out, and then she continued on. But which part, if you take a look at the graph, when was she traveling faster? Was she traveling faster between 0 to 4 minutes, or was she traveling faster between 8 to 10 minutes? And in this case, you can tell because of the incline of the graph, she traveled a lot faster between 8 to 10 minutes. So she was like, okay, I've got a nice walk from 0 to 4 minutes. I'm stopping and taking a break, and she realizes, oh wow, my break was too long, and she speeds up and gets to Katie's house pretty quickly. Hey guys, this is a continuation of 13.3. Last time we talked about distance versus time graphs, but in this one we're going to talk about speed, velocity, acceleration, and how it relates to those graphs. So again, let's talk about speed. Again, it's the distance of an object, distance an object moves per unit of time. So in order to calculate speed, speed is equal to distance divided by time. So meters over seconds. Okay? So let's talk about motion first. Relative motion can be probably one of the most difficult concepts I've seen for some reason for the 6th graders. So I don't know if any of you have ever been on that ride at the fair. Pretty legit ride, I'm not going to talk to you. But what relative motion is, it's the motion an object has in relation to a reference point. So let's take a look at that picture really quick. So you see the 2 kids that are maybe, I don't know, an adult, but there's 2 people on the ride that I can see up in the top right-hand corner of the ride. So when you're on that ride, what happens is that thing spins and it tilts from side to side. And whenever you're on the ride, it actually seems that you're not even moving. And really, it's defying the force of gravity in a way, and you're able to slide up and down on that pad and move your arms. Okay? But look at the guy that's down here on the bottom. And he looks like he's about to get on the ride, or maybe he's controlling it. He definitely sees that ride spinning. Okay, so the people inside aren't necessarily they know they're spinning, but they can't necessarily see it, versus the guy outside who actually sees the spinning. So in reality, the 2 people, the 2 sets of the guy on the outside and the 2 on the ride have different reference points. Okay, so an object's going to be a motion, the relative motion is going to be different for both of those people. It's the same concept of like if you were driving in a car. Okay, so say you were a passenger in the car and you're in the back seat and you have someone sitting next to you. Okay, and Miss Kennedy's got a tennis ball in her hand and she's throwing the tennis ball up in the air and catching it. Well, if you were sitting next to me in the back of the car, you would see the ball going up and down, even though we were moving. Your reference point, we know we're moving, but the reference point is me sitting down at that point. So say we're moving, and on the side of the road, there are friends on the side of the road, and they see us passing in the car. Well, they're going to have a different reference point. They see the car moving forward, and they also can see the ball inside the car moving up and down. So a different reference point. Okay, so relative motion, again, is dependent upon the reference point where you are at. All right, the next thing I want to talk about is velocity. Okay, velocity is different from speed. Velocity is both speed and direction. So on our, for example, our speed limit signs, it doesn't say 65, speed limit 65. It says, that's all it says. It doesn't say 65 due north. Okay, velocity would be my speed plus a direction. So I would say the rooster flies 65 miles per hour east. And that would be the velocity of the rooster. The roosters don't fly. Sometimes. Anyhow. Secondly, acceleration, or lastly, acceleration, okay? Acceleration is just that change in speed or velocity over a specific amount of time. So think about bumper cars. So the way you can define acceleration is by three things. You're either increasing speed, decreasing speed, or changing direction. Now, that means you can have, if you're increasing or decreasing speed, that means you can have a positive or negative acceleration. Increasing speed, if you're moving forward, you have a positive acceleration, all right? If you're decreasing speed, you're technically having a negative acceleration. Now, let's reference back to our distance versus time graphs, okay? What does acceleration look like on a graph? Is it a straight line? Does it go from the bottom all the way to the top in a straight diagonal? Acceleration actually looks like a curve on a distance versus time line, okay? So over time, your speed builds. Think of acceleration of like whenever your mom and dad are driving in a car and they're stopped at a red light, and then the car accelerates forward. It comes from a stopping point and moving forward. All right, on to 13.1, which is forces, and then mass versus weight. Okay, there are two types of forces, contact and non-contact. Let's talk about contact first. All right, contact forces are those that exert an effect by touching. Okay, so when you push somebody, that's a contact force, also known as an applied force. Me sitting here in my bedroom, you sitting or standing, that is a normal force, okay? So just like our little brain, which is a muscle, is standing, a normal force, okay? And then there's also friction. So our little polar bear that fell down over there, there was some friction. Yes, ice does cause friction. Anything that rubs against another is considered to be friction. So there's three types of contact forces: applied, normal, and friction. The other type of force is a non-contact force. There are three types of those. Non-contact forces are those that exert an effect at a distance. There's three types: electrical, magnetic, and gravitational. An electrical force is one where you actually are having positive and negative charges, so electrons. What happens is they become excited, okay, or you will see, for example, like whenever you are on a cold day when there's not a lot of humidity or H2O in the air, what happens is that you are capable of shocking a friend when you touch them in that little small of electric current. Same thing like our picture right there. You see that whenever you rub the balloon, again, you're creating friction in a way. That's a contact force. But from a distance, that's actually an electrical charge between the hair and the balloon. A magnetic force is with two magnets. Now, we all know that how magnets come together, and I wish I had mine here at home, but so I could show you. But the north and the south end, just as opposites attract, have to come together. Okay, so a magnetic force is one caused by a magnet. Finally, a gravitational force. Okay, gravitational force is caused by gravity. So in this example of the young man standing on the hill and the ball falls down when you throw anything up in the air is considered to be a gravitational force. All right, let's talk about gravity a little bit more in detail. First of all, if you have mass, you've got the law of universal gravitation. Okay, what the law of universal gravitation says is that if anything has a mass, or two objects have mass, they are going to attract one another. So in reality, we are attracted to the core of the earth, and also the moon and the sun up in outer space, okay? We don't feel it, but we have mass, and there's an attraction there. There's two things that affect gravity, mass and distance, okay? The greater the mass, the greater the gravitational force. That means as one goes up, the also increases. That is called a direct relationship. So looking at the graph, you see a direct relationship, a positive correlation, right? As distance increases, the gravitational force decreases. So the longer, the further the distance, the force decreases. That is considered to be an indirect relationship. As one goes up, the other goes down. So on your graph, you see an inverse relationship with a down diagonal. Okay? So talking about mass, let's discuss the difference between mass and weight. All right, mass versus weight. Mass is the amount of matter that we have or any object to have. So when we go measure something on a balance, okay, or you go use the triple beam or the electronic balance, you're actually determining the amount of matter in an object. So your teacher should have said, go determine the mass, not the weight. Okay, the weight is the measure of force of gravity on an object. All right, so in reality, we are actually, when we sort of kind of misspeak when we actually go take our weight or our mass. Okay, we should be saying, what is the amount of mass? We can gain mass. You know, some of us are a little bit more heavy than others. And weight, our weight is going to be dependent upon where we are with relation to a certain object. So, for example, our weight, if we're here in Florida, which is equivalent to close to sea level, we're actually going to have a heavier weight than, say, we were up on Mount Everest, okay? Mount Everest, there is, as it says down there, as distance increases, gravitational force decreases. So our weight is going to increase when we live in Florida as compared to Mount Everest. So I'm definitely moving up there. So hopefully that answers some questions so far. So let's talk about balanced versus unbalanced forces. Okay, we're going to start with balanced. A balanced force is when object's motions does not change. So looking at our picture right here, we have two people pushing against a box. All right, at this point, the box is not moving. One is exerting a force in the same direction, no movement. So a zero net force, that's what that's considered, the total sum. It does not accelerate. If you have no net force, there is no acceleration. Net force is the combination of all forces. So let's take a look at this next little snippet down here. So this is a little bit higher than what y'all actually have to understand, but it's a good thing to try to conceptualize this. We are advanced students. So we have a book, and there's one force, F2 versus F1, and they're pushing on one another. One is of 18 newtons and the other is 20 newtons. And you're thinking to yourself, Miss Kennedy, you just said 20 newtons. In reality, it's negative. Whenever we actually talk science, and as you get older and you're older in your higher subjects, you're going to see that the negative actually has to do with direction. So for example, if we're moving in an opposite direction, just as I talked about acceleration with 13.3, a negative acceleration is actually considered to be the inverse of the negative. Okay, so it's moving in the opposite direction. All right, same thing with like cold and hot. If something absorbs energy, so it becomes colder, it's actually a positive relationship. Versus if it gives off energy, an exothermic reaction, an explosion, that's actually a negative loss. Okay, so you would report that as negative. It's just the flow of energy. So let's go to our example. So mind the negative. All I need you to focus on is 18 and 20. All right, so if you look here, 18 newtons is pushing on one side and 20 newtons is pushing on the other. So there's a difference between 20 minus 18 of 2 newtons. Okay, those newtons are going to move in the direction of the force. So the book is going to be moved towards the left. Would you agree? Okay, there's 20 newtons. All right, it is not a zero net force in that case. An unbalanced force, which is exactly what we just talked about right there, is whenever object's motion change, it does change. So our poor little mouse hanging on for his dear life as the elephant sits on our teeter-totter. When forces act in opposite directions, the net force is the same direction as the larger force. So going back to F1 versus F2, that's why the direction was to the left. 2 newtons to the left. Okay, or it could actually be, you could report it as a negative, and teachers could understand that. So in this case, let's take a look at our diagram of our 2 men having tug of war. Let's talk about what's wrong with this picture right now, okay? Well, let's talk about what we see. I see the man under the red arrow standing up, pulling. Doesn't seem like he's exerting much force, but he definitely has the upper hand. Versus the guy under the blue arrow, you can see that he's pretty much putting all his effort in. At this point, there's no determination of where it's going to go because we have no numbers and we don't know which one's stronger than the other. But let's just say that the man in red, the man underneath the red arrow, has more newtons than the other. How could this picture change? How could we show that with just a diagram of arrows? In that case, what we would do is we would draw a larger arrow. The red one would be much longer than the blue one. Okay, so that's another way to indicate force. Talked about 3 different ways, one with negatives and positives, one with numbers, and one with arrows.